All right, kia ora koutou, everybody. Welcome to the webinar this evening, which is focused on a pretty challenging and external demonstrate understanding of processes in the ocean system. This is um, through funding that ESSENS or Earth and Space Science Educators New Zealand provide. And yeah, hopefully we leave you with some good food for thought this evening and ways that you can either improve your pedagogy related to oceans or just lift your achievement with your students in your kura. So I will kick things off with a karakia. This is the ESSENS karakia. So ki raro I te korowai kai te aki o te ketenui a tānei. Mā te hau e pupuhi te pākahu ki o mātou waka. Te kaha tānei, tangaroa, manaki tia mai a tātou katoa. I roto i te hikoitanga i te ao o rangi rawa ko papa he te oranga o mātou. Kia piki aki i o rawa Māori, kia toi mātou i o rawa mana, hui e, tai ki e. And just a quick translation there. I don't have the translation with me, but beneath the cloak of the protective cloak of Tane, and the waka that we're on, let Tane, Tangaroa, and Rangi and Papa let us uplift their mana and their Māori, and so it is. So that's produced by ESSENS, and we like to kick things off with that all the time. So a quick rundown on a plan ahead for the night. We'll do some quick introductions, talk briefly about other resources and support that ESSENS offer. We'll then give a brief overview of the standard as a whole, and then we're going to unpack each of those elements. But rather than telling you what to teach, we thought we'd expose you to the key challenges that students face and present to you a few activities or things that you can do with your tauira to ensure a bit of engagement. And then we're going to round it out with a quick look at what different levels of achievement look like with the very challenging externals. So first of all, I'm Ross Stephen. I teach at Avondale College in Auckland. It's an extremely large school, and I've been teaching Earth and Space Science for this is my 10th year at the school, so that long. So I do have quite a bit of experience with this particular standard. I'm certainly not claiming to be an expert in every area of that, but yeah, hopefully my experience helps you improve what you're doing in your school. I've got an honours in geology. I've been a regional representative for Earth and Space Science Educators New Zealand for, I think, 7 years now. I've also been a panel leader for this particular standard, and I do have some work relating to development of exam questions. So yeah, that's where my experience comes into this particular standard. And now I'll pass you over to Najeen, and she can tell you a little bit about herself.
Sure. Hi, so I'm Najeen. You might have seen me in some of the other webinars earlier this year too. So I work over at Massey High School in Auckland, and yeah, I've been teaching Earth and Space Science since 2014. Particularly the standard is one of them too. It's yeah, pretty much every single year since then. So yeah, like Ross, I've been teaching it probably over a decade. My background's in astrophysics. But yeah, along the way in my university degree, I've did dabble in some geology and some atmospheric sciences as well as oceanography too. So I've kind of dabbled in a few other bits and pieces here and there as well. And yeah, mostly I'm just kind of hoping to help, share some of the things that I have found works really well for my students and hope that kind of excites people as well.
Awesome, thank you, Najeen. And yeah, just a bit more of a plug around ESSENS and what we do. We're just Najeen, since this is one of your areas, maybe you could talk to a few of these things, particularly resourcing. And I'll just flip through a couple of these slides.
Sure. So yeah, obviously the New Zealand curriculum and NZQA is where you'll find the main information for the standards. But on the ESSENS website, you'll find a lot of resources, particularly for oceans, as well as all of the other standards there too. We have PowerPoints and yeah, webinars and all kinds of different things that you can take a look at. I think there are some topic outlines as well, and for many of the internals, there are also some range of ideas as well for what you can do for the internals.
We've also got, well, this year Essence has been doing a whole range of webinars. So if this is the first one that you might have heard of, please be aware there's a whole range of other ones that are on our YouTube channel, and there's probably about 6 more coming across the year. And the purpose of them is just to connect with educators across the motu and make sure that you know, our collective expertise at Essence is trying to make sure Earth and space science is taught effectively in kuras across the country. If you're not a member, the registration link is there, and I'll send these slides out afterwards, so you'll be able to access it all. Strongly encourage you to sign up because there's heaps of resources, and you also get a bit of access to some practice exam questions. And for this particular standard, they'll be available soon enough. I'm not sure on the exact date, but before your practice exams would roll out. I think towards the end of this term,
Yeah,
we're
our
hoping to have
timeline is
them.
end of this term.
Yeah, awesome. So yeah, Achievement Standard 91413. It is a very challenging standard, and yeah, I thought this might be a great whakatauki to actually reflect that. So, he moana puki puki e kingia e te waka. A choppy sea can be navigated. And I guess what I wanted to say about this is that the choppy sea would be the whole standard itself. It's got lots of hurdles, but the waka, which is referred to here, you are, I guess you can guide that waka through the choppy seas. The waka would be the students that you're trying to carry through and get through the standard. And hopefully with the knowledge that we impart on you tonight and additional ways that Essence can support you, you feel more than happy to tackle this choppy sea head on. One of the main reasons why this standard is so challenging is that I guess the earth science itself is an application of biochemistry and physics. And to do the standard effectively, you must know or be able to help your students understand aspects of biology, chemistry, and physics, and earth science and ocean processes as well. Which in itself is a huge challenge because I'm pretty confident that many kura across the country, they may say, no, you haven't met the prerequisites to take biology, chemistry, or physics. You will go into the earth science class, and if they're not bringing that knowledge which is needed to do well in this, then it's going to be really challenging as well. So hopefully as well, with the new physics, earth, and space science standards across level 1, and if and whenever they come out in level 2 and 3, hopefully there's a bit of continuity from what's already been established at level 1, and in the future we might see a bit more of a cohesive or slightly more achievable standard. So yeah, I'll just point out biology. It certainly comes into it when you're looking at the carbon cycle aspects, but also the transfer of matter and energy. Chemistry, I mean, the carbon cycle part itself is very heavy on the chemistry. And physics, many of, I guess, the guiding principles of physics and physical principles, they come directly into the ocean composition section and are scattered throughout. Najeen and I were talking in advance about a best way to maybe approach this, and I just want to flag this: what we're about to tell you doesn't necessarily mean it's going to fit your kura, but it certainly is a good way of approaching the standard. And I'll just flick back, show you there's 5 key elements to it. And I think 5 weeks at a minimum would be what you're looking at. Personally, at my kura, we push that out to about 7 weeks. It does make crunch points elsewhere across the year, but you can see the last bullet point there. But giving ample time for the students to practice, that certainly is beneficial for the external as we reach it. The transport of energy and matter, as you can see here, it's got heat, tides, and waves. But Najeen and I, we were quite keen to highlight that while it's sort of standalone aspect of the standard, it certainly is sprinkled throughout everything in the topic. So I really encourage you, if you're teaching it, to keep highlighting to the students, oh, this is the transfer of energy in the ocean, or this is how matter is transferred throughout the ocean. And another key point, if you are brave enough to teach the atmospheres standard as well, another very challenging external, your students should certainly do a better job of oceans. But I know many schools are quite adverse to trying to externals, particularly ones that may not generate favourable outcomes, like your sort of higher level chemistries and physics. But yeah, I mean, the atmosphere one, I don't know, maybe some others might say it's more challenging. I'd just pitch it as equally as hard. But, you know, a lot of crossover between the two, and delivery of both of them will certainly help your students. And Najeen, just remember to interrupt me if we get any questions as well.
Yeah. Okay.
So, you know, that's a bit of a broad way on how we would look at teaching it. And yeah, Najeen and I both talked to this, but certainly start with looking at composition, what the ocean's made of, how the properties of water change, and that certainly links to the three key layers which are pitched, which is, you know, your surface or mixed layer, your pycnocline layer, and then your deep ocean. After that, you could move into waves and tides, purely for the reason this is all stuff that's acting at the surface. And beyond there, you can then move on to your surface circulation patterns, and then move on into teaching the deep water circulation, or thermohaline circulation as it's referred to. ENSO, if you're unfamiliar, an acronym for El Nino Southern Oscillation, a pattern that's not as only experienced in the Pacific Ocean, but worldwide. But we would recommend focusing on just the Pacific Ocean basin and its effects. And that would also allow you to leave the more challenging carbon cycling ideas to the end. And, you know, carbon cycling and El Nino ideas, you know, if you taught the other three major components first, they get a nice flow, and the students certainly bring a bit more knowledge from those areas and would manage it a little bit easier. So yeah, at my kura, while this is what we put together tonight, I actually teach carbon cycling in advance of the El Nino, but that's because I am at a school that teaches both standards, and I just find that you know, because of how linked El Nino is to atmospheric changes, if I leave it till a bit later and gloss over a few of the more challenging parts of it, I can then reiterate that when I teach atmospheres. But if you're just doing oceans, yeah, it's going to be a lot to cover. So we're just going to go through aspects of the standard now. Like I mentioned earlier on, we'll highlight some key challenges and then present to you a few key ideas or activities that might help your students engage with this a little bit better. So the first part, ocean composition, looks at different gradients in the ocean, and the key gradients are temperature, density, and salinity gradients, often referred to as thermo, halo, and pycnoclines in the ocean. And another key concept, which from my perspective is pretty poorly understood from students nationwide, is pressure. You may have the odd student from a physics background who can do a good job of this, but you know, many students will severely under-explain this, and yeah, it certainly would make them miss some easy achieved points. The main challenges with this, I actually probably should have included this in my list, but defining the keywords, you know, descriptive or definitions of these keywords is going to get achieve level marks for your students, but that's about it. When we talk about the ocean being global, you've got to appreciate latitude, and many students just are a bit clueless to what latitude and longitude, although that's not too much of a focus in oceans. They're a little bit clueless as to what it is. I mean, I can sort of see why. They certainly know how to use Google and Apple Maps. They know how to get places by following the blue line, but maybe they don't appreciate the science in the background, which gets them to that point, which is all about GPS and specific latitude and longitude. So I would recommend taking a bit of time to make sure they know that it's more than just a number, and trying to get them to appreciate where on Earth specific locations are based on the longitude and latitude. There's also huge misconceptions from students on how the Earth and the ocean is heated. Please keep in mind that many of your students, it might have been year 9, or maybe if they're lucky, year 10. It might be the last time that they've actually been taught about seasons or the heating effect of the sun. And we frequently in exams, when I was a panel leader, would see statements like, "Oh, it's because it's closer to the sun," and that's not really going to help the students, pick up any points on the exam. I would encourage them to draw diagrams and just make sure they're aware of the angle of insolation and what that means at different latitudes across the globe. Explaining is in bold. I'm going to come back to this later when we look at an achieved merit and excellence, which links to ocean composition. But yeah, many of the students, they just really struggle to give proper explanations for why temperature, density, pressure, and salinity in the ocean would change. They may identify that temperature decreases, but they're not able to give the reasons for that as such. So yeah, there are a few of the key challenges with ocean composition, but now we'll have a quick look at some engaging ways to try and get them to better understand that. And one way to do that is through practical work. And I guess, the ocean being such a large scale and global, it's pretty hard to do some practical work. Most students, their interaction with the ocean is standing at the beach and dipping their toes in. Maybe some have been snorkeling, a few would have been scuba diving, but that's just such a small part that we interact with. They really struggle to go on the big picture stuff. So Najeen, do you want to talk about this first activity?
Sure. So basically, what I'm sending here is, in the slide is basically a video link that when he sends out the PowerPoint, you'll be able to kind of click into it and it'll show you instructions for the activity. But yeah, one of the things that I often get to do is get my students to really kind of visualize the different layers of the ocean with kind of color coding some of the different densities of different types of water. So this activity pretty much is I set up like a beaker with really cold, very dense water with a lot of salt mixed into it. Then we have another beaker which is dyed a different color to make it a little bit more obvious. So we basically have this whole spectrum of different temperatures with different levels of salinity. And the students pretty much go to each of those beakers with just one of the straws and like a plastic straw, or it could just be a piece of plastic tubing. They go into those right to the bottom of those beakers, sealed with the straw, like kind of the thumb kind of basically covering up the top. They just quickly let some of that water into the straw, and then go to the next one, and then the next one, and the next one. And what happens is every single one of those colors, if they start from the least dense to the most dense, they'll see a different effect than if they go from the most dense to the least dense, or in reverse anyway. Don't remember which way I just said it. Um, but yeah, so what they'll see is on the left hand side there, you can basically see this like perfect little rainbow, and it will stay that way. It'll help them visualize those different layers where your hot, fresh water will be at the top, your more dense, colder, really salty water will be at the bottom. But if they reverse that, they'll see that everything inside of the straw mixes, and it really kind of gets them understanding why the ocean really kind of has this structure and why it doesn't actually mix vertically very much. So it really lends itself very nicely to talking about the how the temperature and the salinity can have an effect on the density and why, we end up having the structure overall.
Yeah, and I personally do this with test tubes, And you can always throw a little challenge in there and say, okay, well now use a pipette or a dropper, and I'd like you to remove, let's say the green layer. And students would then remove it, and they can still see that the barrier remains the same between the two different densities. It takes an extremely steady hand, but set it up in quite a large measuring cylinder. And it's simply just sat in my classroom with no mixing for about 6 or 7 weeks. Depends how much salt you put in to make the contrasting densities. But after a while, it does sort of reach homogeneity and start mixing together. But yeah, like Najeen said, a great visualization and a practical experiment that students can do to um, you know back this composition ideas up. There's a couple more things that you can do as well. Um, I definitely would recommend a bit more practical work on density. You could, as simple, these are still great science capabilities. It doesn't mean that you're not teaching to the ocean's high level, but, getting students to use scales or measuring equipment to accurately infer density changes. And one way you can do that is expanding water as ice freezes. There is a great visualization there, linked in on YouTube, which shows how the water molecules start to bond up and expand, helps you appreciate ice being less dense than water. And in the bottom right there too, just highlighting how rather than hot and cold here, you can also do different salt densities or salt water over fresh water. And without playing the video, the image on the left here, you would either have some gas jars with a lid and quickly slide out the lid. I've actually as well used just OHP paper. Yes, it still has a use somewhere. And, if you do the one on the left-hand side there, very little would happen. You might get the slight air bubble come in and show a slight bit of mixing. But if you compare that to releasing the blue or colder water over the hot red water, you're going to start to see mixing and, currents start to establish there.
Yeah.
I said before, it's hard for students to grasp the scale of the ocean, but these are some nice, easy things that can, at least help model some of the large scale processes that are taking place.
I do find that particular activity that you have there, Ross, too, is really nice because it helps them kind of reinforce that things are being heated from above, and you're not going to get a lot of convection and mixing if things are being heated from above because the less dense layer is already at the top. So there's no reason for this vertical mixing, which helps kind of talk about when you're looking at ocean circulation later on, it helps reinforce that.
Yeah, and aspects of the carbon cycle or physical carbon pumps as well can link in here too. So yeah. Skip the videos. Right, on to the next part, which is ocean circulation. Actually, I might come back to this and just skip ahead quickly to this part, Najeen, just because we talked about doing waves and tides before we move down in the ocean.
Sure.
So I'll just quickly talk to this, and then I know you've got a video you want to highlight a few things. Now, one of the challenges, waves and tides is rarely assessed. And I guess last year, if anything, it was a great reminder that we as educators should teach the whole standard and not just get students to keep practicing past papers. I know many kura would have been caught out by this. Pretty much a whole question was purely focused on tides last year. And I know the results on that particular question were pretty poor. I'm a bit luckier here. I had spent a bit of time on tides, but I don't think my students were able to connect the tides to the global warming impacts that were thrown in on that question. So that was definitely a real curveball. I think about the only time tides has really been a major part of an assessment. ways that you can sort of help improve students with tides is by doing pattern seeking observations or making predictions about tidal heights and variations. Yes, I know there's a whole heap of variables that influence that, but there's also a whole heap of easily accessible data to help students. I guess go and check, was I correct? Is that what it's going to be like? And easy ways to link in fishing, or you might want to go out on a boat, or you might want to catch a ferry somewhere. When is the right time to go? They're all quite easy ways to try and engage your students. And big waves as well. After Najin spoke to a video, I'll bring up a simulation which can help you look at where big waves are across the planet. And it would be nice for students to do a bit of exploration and find where those big waves are occurring before you actually go and tell them about where and why they form in that particular way. So the simulation I'll show you shortly you'll see it at multiple points. If you don't know about it, it's a game changer for teaching oceans. But yeah, a couple of links in here for things on waves, wave interference and ripple tanks, and tides. But yeah, Najin, you might want to quickly speak to this particular.
Sure. So again, this is one of the videos that you'll have a bit of an interactive way to kind of visualize what you're talking about, and the actual video will show you instructions for how it works too. And even though this looks like kind of a Lego tray, in my classroom it looks more like your typical practical science gray trays, where basically students just fill the bottom of the tray with a few centimeters of water. We're looking at how to link the depth of the water to the wave speed. So what they'll do is they'll just create a few centimeters deep of water at the bottom of the gray tray. They'll lift up one side of the tray just ever so slightly and then just let it drop to the bench. And what that creates is this really great wave that just races across the tray and then comes back again. They can get a little bit of a sense for how fast it's moving. So, I have even gotten my students to time that before. I have them, just let it go back and forth 5 times, time how long that takes. They can get a bit of a sense for the wave speed of that. And then we change the depth. We'll like double the depth or even triple the depth, do the same thing, lift up one side of the tray, let it drop. It creates this beautiful wave that you can really see the wave speed, and they can kind of compare how the depth of the water creates the different speeds. So yeah, it really helps us kind of go on to discuss, what's going on in the different depths of the ocean there too. Yeah.
And just another way you could use technology for this. I know phones are banned in school unless you give permission, but maybe you could get the students using the slow motion camera. You could put a few little markers up the side of your grey tray, and just they could indicate, or actually collect some data on wave height as it's changing, and that would be quite easy with the slow motion camera. Now I'll just switch over and just confirm with me. You're seeing planet Earth here with some swirling patterns. Awesome. So this is I call it Earth Null anyway, but it's an absolutely amazing simulation. Amazing for the reason that it's got historical data trapped within it. So since I was talking about wave height, I'll just show you now quickly how we can use that. And hopefully we're all aware that some of the biggest waves are generated in the Southern Ocean. So you can click down here on Earth, and there's so many different sort of parts to this simulation that you can use. So since we're on oceans, I'm just going to come over, click the Ocean tab, and now I've already had it set, but you can look at winds in the ocean, currents, and I'm just going to select waves. Now in the overlay, this is where you can change a whole range of different features. Here's our waves and the currents that are attached with them. And if you've got absolutely no idea what all of the letters are, I'll just show you here. You just hover over it and it tells you what it is. And we just want to look at, we want to have waves on, but I want to show you significant wave height. Okay, so we can now start to navigate the planet. And, we can clearly see that around the Southern Ocean here, you've got your biggest waves. You've got little scales here. They may not be that useful just with color, but an awesome thing about this particular tool is I'm just going to zoom in on the biggest wave I can see at the moment. As you zoom in, you find a spot of interest, you just click on it, and above all that data on the left-hand side, it gives me a pretty accurate indicator, first of all, of our longitude and latitude. We can link students back to that challenge I said earlier on, but it also gives you an approximate range of there's an 8 meter, 8.4 meter swell in this particular location at this time. Okay. If you are aware of big storms that have happened nearby your school, wherever you are, which coast, another cool feature is you can click the little calendar here and you can go back about 12 years in time. I'm not saying all the data is absolutely perfect, but on the same day last year, we can just change to that. It may take a moment to reprocess, but we can see still in the Southern Ocean, we got 10-meter waves at that time. So it's a great exploration tool.
So,
And
Ross, there was just a question that popped up too. Sorry.
okay, yeah.
The question was from Nikki. Nikki was asking if do you prefer this to windy.com? Now, me personally, I end up using both. I find there's pros and cons to both. What about you, Ross?
I much prefer this. I still would use Windy, but that's something that I would more use when I'm teaching atmospheres. They do have similar features, but for me, I think this is just a little bit more powerful when we're teaching oceans, purely for the historical stuff that you can capture and all of these different features that you're looking at.
That you can
So
change. Yeah.
yeah, Windy is still a good source, but yeah, I might just use that a bit more when I'm teaching the atmospheres topic. But yeah, great question. If you're unaware of Windy, certainly still check that out. Similar features too. Yeah.
And
All
Bruce has
right.
also asked if there's any other tools that we use for oceans.
In this particular simulation, I mean, I would also look at surface currents and
Mhm.
you can match it up with the air. I'm on the air simulation now, so it's showing where the winds blow. You can
I
switch
also look at El
nicely.
Nino and La Nina on there too.
Yeah, we'll come back to this when we do look at El Nino and La Nina. But
Yep.
we've already talked about circulation. You can see the air patterns. You can then switch over and see what are the ocean currents doing. Are they matching up with the air patterns, etc. So yeah, still a useful tool. But yeah, if you prefer windy, um, go with that one as well.
I agree with
Right,
you. It's the power of the historical data that is really quite helpful for that one.
yeah. And just before we move past this one too, I know it has popped up every now and then, but it links back to what I mentioned earlier: sprinkling of transport of energy and matter throughout the ocean system. You could as well introduce here some floating debris and start to sort of see that it's actually waves are moving energy and it's surface currents that really move matter around the planet. So if you introduce something here, a wave may pass and it should relatively stay in a similar position, but because of I guess the short length of the wave traveling, you may get quite a bit of disturbance and it may not turn out perfect, but still a good way to reinforce that concept, which is frequently an achieved level statement of waves moving energy, surface currents moving matter.
Mhm.
Um, anything
Is it
else
okay if
on?
I chime in on something on
Yeah,
tides?
yeah,
Just real fast, because people have asked me a few things about tides too. Particularly obviously looking at like, things like, neap tides and spring tides and things that kind of come back to the level one standard. A few people have asked me in the past, like, do we actually talk about, how this is not the full explanation? And I said, I personally do. I don't know that if the standard really requires us to go deeper than just the sun, moon, earth kind of explanation. But I know I personally, because my students often live near a coast, they know that their high tide is not the same time as somebody that is farther up north or south and from them. So I do pretty much talk to the Earth, Moon, Sun explanation as being like, yeah, the trigger behind it rather than the full explanation of timing. And then we just kind of talk about like why spring tides and neap tides and things, why they're on this kind of 2 week, 4 week cycle, depending on what it is you're talking about. And yeah, if people are interested to go into the deeper explanation, they can look up the dynamic theory of tides. But I do tell my students that that's an extension, but it helps them feel a little bit happier about the explanation behind things.
Mm. Yeah, and great point. Surely we all live near where the tide goes in and goes in and out.
Yeah.
I'm not saying take a field trip, but encourage your students to get down to the water and have a look at it. Um,
Nikki
yeah,
has also asked if we need to link in the Coriolis with tides. Uh, I think I haven't seen very much with like tides and Coriolis effect together. Have you? I think it's
uh, per-
mostly like just that sloshing, isn't it?
yeah, I personally haven't seen it myself, and I know um, if we consider the tide as one giant wave across the ocean, there would be some deflection at some point, but I'd probably restrict the Coriolis effect idea to the direction that the surface currents are moving.
Yeah.
That would be my recommendation. Um, and yeah, I'll definitely talk about Coriolis effect soon. Um, yeah. Um, but yeah, I think just before we move beyond waves, the only other key thing which I'd raise is there's been a few key words every now and then come in around waves, more what causes them to form, and fetch is something which is pretty common, and fetch is purely undisturbed distance that a wind can blow. Wind duration
Mm.
is also pretty key. If a wind blows for much longer, it's going to generate bigger waves. And just a quick flick back to here, we can see that if we're looking around the Antarctica, enormous fetch. The wind can blow in that, around the Antarctic continent, undisturbed for thousands of kilometers. Also, significant pressure differences, so you're going to get really high wind speeds as well. And that's why we would see those giant waves forming around there as well. Right, just get back a little bit now. Yeah, so I guess at this point we've looked at what the ocean's made of, what's happening at the surface to an extent, and now we can start to explore circulation. So some of the big challenges, and thanks Nikki for bringing up Coriolis effect. First of all, is its definition. I know that across atmospheres and/or oceans, pretty much every single year, a student could put a good definition for what the Coriolis effect is and walk away with an easy achieved point. But frequently the definitions just aren't up to scratch. They'll say that it's a deflection, but they won't give a reason for what the deflection is caused by and how that impacts the ocean body. Other key problems with surface circulation questions are staying on track. And sorry, I'll just bring up my notes that I wrote about this because I thought it was quite key. I've mentioned that, surface and deep water currents, they have similar mechanisms. It is often about change in water temperature or salinity, but students struggle to make that differentiation. And quite frequently, they'll, on a surface currents question, be talking about water moving along the deep ocean. And, while they may be accurate, they're certainly not picking up the points at the achieved level there. Also, knowing the role of boundary currents is quite key, or what land masses do to change ocean circulation patterns is quite essential. And I just added this a little bit later on today, but what the actual role of ice is, and a couple of key things around ice is that yes, where it forms, it does promote deep water circulation by making water really dense below the surface. But it also has a huge impact with albedo. And what that does is it helps maintain cooler surface waters. If the ice reflects a lot of the sun's light. So if we've got less ice, we're actually stopping downwelling itself, but we're also heating up the water a little bit more, which reinforces the slowing down of those deep water currents. There's plenty on downwelling. Much of it is focused in the northern hemisphere on Greenland. We do certainly get the thermohaline circulation patterns start, but please don't forget about the importance of the Southern Ocean and Antarctica. There just isn't as much out there pitched at the sort of secondary school level for students to, well, sorry, students and teachers to use. But yeah, let's try and keep things Aotearoa or Pacific Ocean focused as much as possible. And there certainly is those same processes happening around Antarctica that are driving deep water formation. Anything to add there, Najine?
No, not at the moment.
Wonderful. Hopefully we don't get an ad here, but I'll just load it up in the background because this video is great.
Yeah.
Yeah. Wonderful. Nice, simple. You just got a bit of water here. Not sure what's sprinkled on it, but you can sprinkle.
Tea leaves.
Yeah, bay leaves. I was going to say oregano, anything on there.
Yeah.
And you can just see this is all equipment you can have easy access to. Just a straw here. And this, at a minute scale is essentially circulation across the ocean. And we'll watch it a little bit longer because we now introduce an object which acts as a barrier. Sorry.
Hmm.
And you can see the change that causes nice and easily there.
And I like extending this with some deeper bowls too. Like if you have deeper mixing bowls, they can see some of the tea leaves at the bottom, and then they'll see some tea leaves kind of floating at the top. And what's
Yeah,
interesting is when you're blowing across the top, they'll just see the top ones move while the bottom ones stay perfectly undisturbed. And it really lends itself quite nicely to comparing surface versus deep water currents there.
yeah, awesome. And yeah, I mean, there's a lot that you can look at in terms of Gaias. And encourage the students. It may need you to direct them that way, but to explore scenarios where ocean currents are used. Pretty disastrous, a missing plane, but when that Malaysia Airlines flight went AWOL, it took a good year, but the use of ocean currents has I know they still haven't found the plane, but the use of ocean currents and their nice slow movement across the surface. There's a lot of mapping of or reversing of those features to try and pinpoint where exactly that plane might have gone missing. You may have seen as well some past paper questions. I know there's been one on rubber ducks, contain a load of rubber ducks disappearing, and that being used as sorry, the students are annoying me that way. A nice way for students to explore how we understood the development of these ocean current patterns. And there's a whole range of other scenarios. People missing at sea. I know, if you know of Norm Hewitt, he spent about 2 days bobbing around the Kapiti coast after he got left behind on a diving expedition. They used the currents to try and track him down or figure out where he might be. And I think it was close to 48 hours he was at sea, but he survived. I think he had a lot of sea lice at the end of that. But that's all stuff that might interest students. I also had a student tell me that there was cocaine washed up on the shore of West Auckland at one point. They said that must have been the ocean current. So if that's what it takes for students to get engaged here, go with it. It's certainly a lot easier to explore the surface currents compared to the deep water ones. And I'll just flick back to it one more time because you can sort of follow these ocean currents here, have a lot closer look. I'll go around New Zealand, and you can sort of see that sort of generalized pattern, but also a lot of swirls and eddies forming. At the bigger scale, you should be able to pick up the big ocean Gaia formation in both hemispheres as well. Oh, sorry, I'm still on there's our currents. Okay, so yeah, still on that. Still definitely using that earth null. And I'm unsure if Windy, just going back to that one, has that sort of same level of detail to it for the oceans.
I just remember that there was a link that discovered just last year, and I'm trying. If you heard me rapidly typing, I was just remembering it, and I'm trying to find it again. There's actually an ocean current simulator. It's made specifically for the tracking of plastics and just to try to simulate it. But I'll find that link and I'll quickly pop it into the class, or not into the class team. I'm so used to being a teacher. Into the chat. I'll put it into the chat. And what it does is it allows you to just drop a simulated little thing somewhere around the coast of Aotearoa, and you can watch the surface currents kind of track it as to where it would end up, which is quite cool. So I'll
Oh,
find that
cool.
really fast and pop that in here since it just came to my head. Sorry.
Oh, that's cool though. Kind of like, I mean, I know well before texting and stuff, didn't you used to throw a bottle in the ocean with a
Oh, of
note in
course,
it?
yeah.
Yeah, I don't know. Maybe some of us are able to talk about that, but I've also got this link in there. If your students do struggle with Coriolis effect, this is a cool tool for them to explore. I'm not going to open it now, but you can change hemispheres you're in. You can move to the poles, or you can start at the equator. And basically, as Earth spins, it shows you with these different arrows the path it should take, but the real path it will take. And it's really a good way to look at I guess one misinterpretation students have with the Coriolis effect. It's all about the direction that you are traveling from. So you will see, I guess, just saying things move to the right in the northern hemisphere. If you're coming from the poles back towards the equator, you still have that right deflection, and many students wouldn't get that without seeing, I guess, a simulation. So yeah, have an explore with that later on when I've sent out the slides.
It looks like one of our
Um,
guests also had that same link, so we've just popped it into the chat, so people can take a look at that too. But it might be worth we can just pop it into the slides later on too. Sorry, it
yeah.
just came into my head.
Najeen, just also email that to me before the end, and I can send it out with a follow up
Yeah,
and the
yeah.
slides and stuff. We'll go to Enzo quickly. El Nino. So yeah, just like the ocean standard itself, this is a real tricky beast. There's a lot to learn, and one of the big challenges is that students might put together a really good looking answer, but it's focused on the atmosphere, and unfortunately, that's just not going to pick them up many marks in an ocean's response. About as far as it might go is talking about how a change in wind patterns drives El Nino and La Nina. Um, so my top tip is that you would teach normal ocean conditions for the Pacific Ocean basin. You would put real emphasis on that, because if students are asked about just El Nino and they learnt La Nina, they're a bit screwed. But if they focus purely on normal and then realize that, oh, I could just talk about the reverse of that for El Nino, then I should be able to pick up at least achieve level points. Or if it's a La Nina question, I should easily be able to talk about how it's a lot stronger. There is times, however, though, that it's a straight compare and contrast El Nino and La Nina, and the key things in terms of ocean conditions that keep coming up is what is the sea level differences across the Pacific Ocean basin? How does the sea surface temperature vary? What happens to the thermocline depth? And then the sort of higher level excellence idea, which links all of those together, is what's happening with nutrients or upwelling and how does that impact marine life. Okay, so this is going to be a great time for us to switch back over to the Earth Null feature. And Najeen, off the top of your head, I think 2021 might be a good year, but you've got an El
Yeah, y'all got
Nino.
floods.
Yeah. Um, just go to oceans. Actually, I'll just refresh the page, start fresh.
Hmm. And that
We
sea
have it.
surface temperature anomaly overlay I really like for that too. The
Yeah.
SSTA.
I'll just show you the sea surface temperature
Yeah,
for starters. So you'd
yeah.
certainly see, and you can click thereabouts. There you go. It's pretty warm over in Asia, 30 degrees. But if you're teaching El Nino pretty well, you'll look at temperature anomaly, which I guess, is long-term temperature variation. Is that about right, Najeen?
Yeah, it's like
Yeah,
the deviation from the norm. So if it's looking warmer in a particular spot that's warmer than normal,
yeah.
yeah.
Standard deviation-esque, I guess. And scientists would say El Nino or La Nina is going to kick in. I think it's when you've got about a degree more than normal. Um, so just going to zoom in over here to I guess off the coast of Ecuador and Peru where it all kicks off. And yeah, I think it's 2021 a good
It's
year.
early 2021, January, February,
Yeah.
I think.
So we'll just have a quick look. I'll just show you. Here's sea surface temperature for starters. And if you go month by month, what you would see is the change in El. Is this an El? No, this is a La Nina year. Correct me if I'm wrong, Najee.
Yeah, it was a La
Yeah.
Nina year.
So La Nina heightened conditions, so trade winds stronger. They'll blow more of the warm water across to the Asia part, which allows more upwelling. So your students should easily be able to track that with the color changes. Um, but again, you can
So you can
sort
see a
of
lot more blues there.
yeah, a lot more
Mhm.
blues. So cooler, and that makes sense, right? Stronger than normal, blowing more of the warmer water across to Asia. We were certainly seeing, variations, 1, 2 degrees, a dead set sign that La Nina is going to be taking place. So yeah, awesome tool. Unfortunately, it ends at 2013. There's certainly bigger El Nino events preceding that, but you can't explore that with this particular feature. But I did as well include a few links here. There's a couple of teachers' guides and the NASA data page here. It's got some good graphing activities. Again, things that students can always improve on. Some good graphing activities which you can explore some slightly older El Nino and La Nina events. So yeah, it's tricky, but like I said, the whole ocean standard is. If you're going to teach atmospheres like I do, I really just leave the mechanisms for change out of it until I go and teach the atmospheric circulation ideas. Um, which now will lead us on to, in my eyes, the more challenging part of the ocean standard, which is carbon cycling. Um,
Sorry, Ross, a question did just pop up too, which was from Nikki. And Nikki's asking, do they need to mention Ekman transport whenever they talk about upwelling or only if it's specifically asked?
Um, students could. I would certainly teach it, but it isn't often an assessed part in the standard. But the mechanism of Ekman spiraling is what is driving upwelling, and it does have strong links to, I guess, the Coriolis effect and deviation of surface currents. And we mentioned boundary currents as well. So if you look into boundary currents, you'll know that, let me get this right, on the eastern side of continents, you're going to have winds generally blowing off the coast. And what that's going to do is drive upwelling by Ekman spiraling, uh, drawing water up to replace what was pushed off the coast. At your western boundary currents, you generally have water piling up. Um, am I? I think I'm saying the right thing. At the western boundary, you got your water piling up, and what that's doing is driving, I guess, a bit of downwelling on those coasts. Sorry,
I think you're
east.
thinking of eastern and western
Yeah,
boundaries of the ocean. Yeah.
apologies, got that
My students
mixed up a
confuse it a
little.
lot too. It's
Yeah,
hard because you kind of talk western part of a continent, eastern part of an ocean. I have to say that a lot.
yeah. I good. Thank you for correcting me. I'll focus on the
It's all
East
good.
Australian boundary current, where you do have winds pushing water over that direction. So you would tend to get piling up of water, and then that would drive a bit of downwelling in that particular area. So yeah, great question. I hope I've answered that. Ekman spiraling certainly challenging. I'm not going to be asking my students to try and draw diagrams for that, but I would give them some good um, good
I
diagrams
feel
to
like it would
support that.
probably lend itself pretty well to like a merit point, like if they're able to link that into upwelling and downwelling pretty well.
Yeah, and again, sprinkling of transfer of energy and matter.
Hmm.
Ekman spiraling is what's, I guess, helping nutrients move from the deep ocean back to the surface. And it might be something that they can link into, I guess, El Nino related questions too. Yeah, so I know we're nearing 8 o'clock, team. We're not too far off. I'll try and make this part speedy. But why this part's so challenging? Excellence requires great use of chemistry from students. And like I pointed out early on, we typically don't get chemists. If we do, this might be their strong point. They would use balanced chemical equations to show what's happening with carbon at each step. Um, but ideally, the sort of question you get on carbon cycling is just about what the physical pump is, or what the biological pump is. One way you can help students improve here is by connecting it to other standards. Um, I would flag, though, it's pretty hard to get reliable and accurate data out of ocean acidification, but it's certainly a good thing to explore if you are teaching the practical standard. And the same can be said about socio-scientific issues. If you've taught oceans, your students have struggled a little bit with carbon cycling, don't tell them to do it, but encourage them to pick something that's going to benefit them for their oceans external. And I certainly give encouragement to many of mine to consider writing about ocean acidification. You'd hope if they can put together a pretty detailed internal assessment, they can at least remember aspects of that they could apply to an exam question. Um, there's a few practicals you can do. Um, well,
Oh,
the
do you want to nail
videos
that?
the video certainly was there earlier, but basically performing ocean acidification in a cup just require a bit of warm
Oh,
water,
Thymo
cold
Blue.
water, a few plastic cups, a bit of acid, and if it generates carbon dioxide, being slightly denser as it bubbles up and out of your top cup, it's going to
Hmm.
start to change. You'd need some indicator too. Sorry, it's going to start to change what color the indicator goes. A good
Yeah.
inference of change there. Yeah.
Yeah, so I do that one quite a bit. It's pretty much like it's a baking soda carbon dioxide one inside of a little bit of like a, I don't tell them it's a shot glass, but they know it's a shot glass, and it's just sitting inside of a larger cup. So the baking soda carbon dioxide generates the carbon dioxide, which then diffuses into just normal water below. And the water below it just has bromothymol blue, and so as the carbon dioxide kind of goes into the rest of the cup, it's all sealed off, and it bit by bit diffuses into like, kind of like the top layer of that water. You can see it turn kind of yellowy, so they can see that it's diffusing into the top.
And I mean, you can even just, using a straw, blow a bit of your exhale breath in, and
Yeah,
with a bit of universal indicator, it's going to change it from, I don't know, it depends what pH your water is coming out your taps, but it's going to, after a few breaths, going to change it to show it's become weakly acidic. Um, so yeah, in terms of practical standards, I have had a little. The video's back again. I have had a little bit of success with students looking at mass change of Nautilus type shells, but it requires quite a bit of time, soaking in solution over a long period of time, and then drying things out, and then looking at mass change percentages. Um, I think a pH of 6. So a student might have used some barium chloride last year. No, that might have been an 8 to sort of model normal ocean conditions. We used distilled water and vinegar. And, the mass change with vinegar, it certainly was the biggest, but also you could clearly see the impact that soaking in just vinegar had for a number of weeks. But yeah, like I said, it is a real challenge to get reliable data for that particular standard, um, but a good thing to explore as well. I see a couple maybe questions before we get to the
yeah.
last part here, Najeen.
Just yeah. So basically, the question that came up is, if you change the temperature of the water in that activity, can you see a difference in the rate of the indicator change? I've found it a little bit tricky to do that. I find it's kind of a slow process to begin with, that diffusion. So what I have done is, yeah, I would kind of leave that to a separate activity, is what I was quickly answering back. And that second activity was that little diagram on the bottom right, which is a little bit of soda water. It's surrounded in like a cold water bath versus a hot water bath. They can really easily see the bubbling happening and it's in a hot water bath versus in a cold water bath. So it's a super quick activity, but they can really see carbon dioxide very quickly coming out of solution there.
Mm. And yeah, I guess a strong link to like those more challenging or harder questions around climate impacts. If we've got a
Mm.
warmer ocean, we're not taking as much carbon dioxide in, which warms the atmosphere more, which warms the ocean more. A real sick cycle, that one. So yeah. I'm just going to jump to the last little bit, team, which is try to unpack what the difference between an achieved merit and excellence look like. And in our little talk about composition of the ocean, I mentioned students do really struggle to give reasons for what's happening. So this is a question from 2022. I mean, you got an achieved point for correctly identifying, I think it was 2 out of 3 locations where upwelling and downwelling might occur on this diagram. If your kids can't do that, then I'd say they're not going to pass the question overall. But I just want to focus in on that second bullet point, explain the processes of upwelling and downwelling. And I've taken a few student exemplars. So first of all, achieved. Remember, it's just about making descriptive statements. So here we can clearly see the student, it's not great, and this is just a snippet. They've said downwelling, they've linked it to density and made an attempt to say what it is. And that's awarded an achieved point. They did go on later to talk about upwelling a bit better, but I've just highlighted on the downwelling side of it here. So a good link to density, but descriptive at best. Onto merit. We've got here that it's starting to supply reasons that support relatively accurate statements on density. This particular exemplar, which is available on the NCA website, it's not perfect from my perspective, but you can start to see they're talking about the angle of the sun, how that's going to change the temperature, and then starting to talk about how salt is going to change the mass of the water and therefore its density as well. I left a few bits off later on, but yeah, relatively accurate statements supporting reasons for what downwelling is. And then we get to an excellence. And yeah, I'll just point out here, this is high quality in my opinion. Firstly, the students clearly said what downwelling is. I mentioned, my students, I'm like, just define the key words that are there. That might be enough. Might be enough for achieve, not excellence, sorry. But clear definition of what downwelling is. Then you can see here, they're starting to say how salinity links to a density change. Later on, they talk about how temperature links to a density change. So that's multiple reasons supplied. But the good thing about this one is they're explaining it at a molecular level. So you'll see the big chunk of yellow later on. I'll just read it out. Lower temperatures means that the water particles have less thermal energy and therefore less kinetic energy. They aren't moving as fast. They're closer together, and that means the volume's decreased, higher density. Okay. I think that, it's only a snippet of their overall response, but it's a really nicely scaffolded response from a student to pick up those excellence level points that are present there. There's not too many of those student exemplars available online anymore. It's possible, Najeen, I'm not sure, but we might have a few more of them stored away on the Essence drive.
I can take a look. I'm not sure, but maybe.
I think there's only about 3 years of student exemplars available at the moment. But yeah. So yeah, I think, I hope that's just helped you appreciate the sort of depth that the students need to go through to get our excellence grades, which are pretty rare. I'm unsure on the stats
Yeah,
last year.
it's pretty hard.
Yeah. Yeah.
I do find I do think sometimes it depends on the students. Like the literacy of the students can make a huge, huge difference. And so for some of my, shall we say, students that are less confident at writing paragraphs, like my school has a big push on the Peel paragraphs, and in like the last 6, 7 years, I ended up adopting it quite a bit for ESS because
Mm.
the point and the example for a Peel format often is they're achieved, and by the time they're explaining it, that's their merit, and they're linking at the end is the excellence. So when we practice that over and over during the year, and I find that usually by the time they're looking at that linking statement, they're often moving in from the merit into the excellence. They can feel that kind of shift in the depth of their understanding. So it's something I've been practicing with my students that are a little bit less like, the essay writers that are,
Yeah. And I guess if you're not doing Peel, maybe next year all this change at level one literacy, you're just
yeah,
going to be generating excellent students left, right, and centre. Maybe.
of course.
So yeah. So yeah, we're almost at the end here, team. Um, but I thought a good place to come back to and reflect on would be this whakatauki. He moana puki puki e ikinga e te waka. Choppy sea can be navigated. Help those students navigate this really challenging standard. And if you are really stuck, maybe Essence, myself, we could be a life jacket for you. Just keep you afloat long enough that the support that we've got and that we can provide you can get your students through. If this is your first year teaching this particular standard, um, I know how challenging it is for you. Just know that with a bit more time and experience delivering it, you will certainly get a lot better yourself. And I know my time teaching it, I've started producing excellence level students, got a scholarship recently. And when I first started, I was running like 50% achieved at best. It was pretty demoralizing. But yeah, I've certainly improved a lot, and yeah, I feel a lot more confident with the delivery of it. So before we finally wrap it up, any final partai there?
He's
Um,
just chimed in saying, brilliant, thanks so much.
awesome. Yeah, and if you do think of partai later, there is an opportunity in the evaluation form for you to leave those. We will reflect on those, maybe not immediately. We've got a few fires fighting at schools, I'm sure we all do. But we will get back in touch with you if you've got specific questions. But please remember to reach out and let us know. All I ask with this evaluation form is that you do give it 10 minutes. Part of the feedback that we collect, we have to produce to the network of expertise. It justifies them giving us funding to put events on like these. And it does take a bit of time in the background for us as Essens and regional reps to put these on. So yeah, your feedback is appreciated, particularly if you've got comments that help you reflect on a change in your pedagogy towards teaching this. It's really important. Or just us as presenters as well. We've got more of these webinars coming, and if we don't hear things, we just might roll the same thing out. But maybe you've got something better you want us to look at. Um,
There was
yeah,
one more question that quickly came through. Sorry, it was just kind of at the tail end there.
that's
It said,
right.
how do we scaffold in junior years? So
Mm.
how do you scaffold in junior years at your school, Ross? I think we probably
Well,
all got different answers to that.
yeah, unfortunately, I'm not in charge of junior science here. Um,
Hmm.
it's pretty static, and I'll be honest, I don't like it. Um, and I'm actually quite lucky. Well, I'm shooting myself in the foot here. I'm lucky. I'm not teaching juniors this year, but that's because I'm well over timetable teaching too many senior classes. Um, and we really don't have a lot of earth science in our junior curriculum. But we're lucky that we've introduced the human induced changes standard into level one. I have a bit of control over that. I think it's a great standard, gives you a lot of flexibility, I guess, to scaffold into your level two courses, which would
Yeah.
then lead on. But as far as juniors, get in touch with your junior lead team. Things I would
Yeah.
push that would be beneficial for your students when they get to level three would be things like, I guess, electromagnetic radiation, what that does at the surface of the Earth, and just making sure that if there's physics in there, that some of those key terms, temperature and density, that your students have a good understanding of it before they reach level three.
Yeah,
Any,
I would say it's the same. So like at my school, it's all of the four strands basically filter right down to the junior school. So I'm in charge of aerospace science, but it also means I'm in charge of the aerospace science part of the junior school. And so what that looks like for us is we don't really necessarily teach oceans per se, but we do teach a little bit about like how much water is on the earth. Water is a resource in general. So we kind of look at like fresh water and how it's a little bit different from salt water. And we mostly just kind of introduce the idea of how surface currents do kind of, are involved obviously in the sailing of moving around the planet and how long that kind of takes. So it's much more surface level kind of ideas. And then, yeah, in terms of foundation science concepts, density is huge. Yeah, pressure, that kind of stuff is huge as well. And then, yeah, when we talk about light and heat and the physics part of our junior topics, that lends itself a long way to talking about it in the senior school.
mm, awesome. Well, we have gone a little bit over time. Thanks for your patience, but yeah, there's so much to get through. We really probably have just skimmed the surface of what's there too. So yeah, I'll draw it to a close. I will point out that shortly after this, the recording will be available. It will go onto YouTube. But immediately after this, I'll reply to the link that I sent out, and I'll attach the slides. And you'll be able to access all of those simulations and links that we had throughout. Um, so yeah, I'll close it off with karakia whakamutunga, ka whakaaeria te tapu, kia wātea ai te ara, kia tūriki whakataha ai, kia tūriki whakataha ai, haumie huie taiki e. And the translation for that team basically says restrictions are moved aside. It's time to go and enjoy your evening. There you go. Time to return to everyday activities. I'm going to head home to my children. And yeah, I hope you all have a good night, and I hope it's been really beneficial for you. And a final plug, if you teach stars, planets, and moons, Najeen will be back next week delivering you more. And we'll be teaming up again early in term three to give you a bit more of an overview of the atmosphere's standard. So thank you so much for joining us, and we hope it's been worthwhile. And
Yep.
going to stop the
So
recording.
much
So
for coming along.
thank you very
Great
much.
work, great work, guys. Najee and I will be back next week.
Oh, yeah, sorry, and Bruce as well. Yeah.
Bruce too. He's
All
along
right.
for this ride.
Thanks all.